Okay, to most everybody here, we don't need to introduce John, because John is here more than I'm here.
John who?
John has, I think you probably have the world record for the visiting scholar duration here. 16 months. John has had a long history, doing many things, but probably most interestingly started with his PhD thesis work at Lamont, where he ended up on an ice island. This was before they had icebreakers. This is back in the days of sailboats, and people would actually get on ice islands and drift with them. And what was it, 13 months?
Yep.
13 months on the ice island. What? That's right. What?
It was like you did.
This explains an awful lot. But John has drifted from doing Arctic work in his early career to all kinds of very interesting bathymetry and DTM creation, and a great supporter of JEFCO. But in his towards retirement,
Salad days.
Salad days. Has basically fulfilled the dream he's had, and that's finding a way to explore the least accessible regions of the Arctic. And to do this, has purchased a toy, a boy toy. How many Ferraris is that one?
This is four Lamborghini.
4 Lamborghinis, worth of a toy. That really, it was interesting. It's been interesting watching this, because there were lots of people who said this is crazy. It just will never work. But, all of it. Yeah. But it's working. It's working really well. I've gotten a report to us about it. I'm not going to try to say the name of it, just so I never get it right.
SABVABAA.
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 SABVABAA. Yeah. Same with that seamount. South of Cyprus, it has a name.
North Coston.
There's that. Okay, go ahead.
Okay, for some 4 years I've been reporting on what the SABVABAA has been doing, and first of all, to explain the name, the money for this came from my grandfather, who was head of the American Chicken Company. During World War II, there were 16 million Americans in uniform. There were K rations and C rations. They got cigarettes and chewing. And for that, I'm very thankful, because this has allowed me to indulge in all kinds of things with JEFCO and the Arctic and other things that otherwise I certainly couldn't have done as a civil servant working in the Israeli government. Initially, the idea of the SABVABAA was that there would be 2 crew members, 2 ladies, who were Norwegian graduate students. My sister recommended the name Chicklet with a K, because of the cross-section of what this looks like from the air. On the other hand, Nina Mikkelsen from Copenhagen strenuously said that working in the Arctic, this had to be an Inupiaq name, and so we went looking for a word for hover. And the closest thing to it was SABVABAA, which means to flow swiftly over it, which defines pretty well what the hovercraft does. And I will go through sort of
In no particular direction.
I will go through more or less the history of what led up to the decision to do this, and cutting back a little bit and trying to aim at what our future directions are, which basically are to find the oldest sediments that you can reach with a short core in the Arctic Ocean. And you all know the Arctic Ocean. This was taken from the 61 centimeter JEFCO globe that you're going to be getting sooner or later from China, which is on its way, more or less. In any case, the Healy has been operating more or less in this area, and last summer we went up through this area. The area that is our target is this area here. This is the Lomonosov Ridge. The Alpha Mendeleev Ridge is 15% larger than the Himalayas in area and about a third the height. And so, first, Yngve Kristoffersen, who is the brains behind this, in many respects the bronze also, I'm a Czech writer, history of having worked on drifting ice stations. And between 1937 and even today with North Pole 36, the Russian ice station, much of the work in the Arctic was done from drifting pieces of ice. In the case of T3, this was a target which showed up because it was different from the sea ice on flights of B-29s from 1940 on. In 1952, Joe Fletcher in the Air Force convinced the Air Force that it would be worthwhile landing on this and setting up a weather station for the Arctic back in the days when the idea was to fly across the Arctic Ocean and bomb Russia in the event of a war.
John, are those ponds on there?
Yes, these are melt ponds in the summertime, but this is sort of a ridge and valley type topography that you have in the ice shelf, which was connected to northern Ellesmere Island next to Greenland. And so during the IGY, Station Bravo was set up here, and as of 1967, these were the remains. This is a very good indication of what happens with an ice station. Originally, the ice was perhaps 60 meters thick. With sea ice, you melt off a meter and a half every summer, and then you freeze it down underneath, and you add a bit more. In the case of the ice station itself, you lose about a meter off the top of pure glacial ice, and you don't replace it. So anything which protects the ice underneath from ablation from the sun winds up getting higher and higher and higher. We call these ice pedestals. As a result, the camp that we were in every single summer, there was a traumatic moment when basically we would have to pull it off its pedestal, knock down the pedestal with a D6 Caterpillar tractor, and then put the building back. This was basically my thesis, which was the last period of occupation here for over 4,000 days. Overall, T3 was occupied for 7,200 days, and I doubt very much if the total amount of time that Ely has spent in the Arctic is more than, 300 days? 350, something like that. In any case, the area that is going to be of importance for us in the future is up here. And this is the drift rack from 1962 around to 1966, 67, 68, 69, 70, 71, 72, 73, 74. As of 1970, I had completed my PhD thesis. I had married an Israeli scientist and made Aliyah to Israel in December 1970. The interesting thing is that data from a seismic profiler that I made, which was operated intermittently, was never analyzed for this area here. In the latter part of 1974, the station was abandoned because it had been sitting off Ellesmere for too long. And of course, the transition from the Air Force to the Navy was occasioned by the Navy having developed atomic submarines with missile capability, and so the Air Force no longer needed to know about the Arctic for flying across in order to, in the event of hostilities with the Soviet Union. So this is a view of what the station was like in 1967, and off here we had a protected bay called Colby Bay with about 6 meters of ice, multi-year ice there, with various hydro huts on top of it. This is one of the huts that took one of the oldest cores that I'll be talking about. The edge of the ice station is along here, and so we have about 40 meters of ice here, 6 meters of ice there. This was the Lamont Palace, given that name because it was anything but where I worked, and you'll see some slides in the interior of that. This is the seismic profiler that I built as part of my thesis work, and it was based upon Korean War and post-Korean War fax machines, which Lamont was converting into seismic profilers and using with NDK paper. And they either had a 6-second or a 10-second sweep on them. As soon as we set this up in 1966, there was a real problem because General Motors Defense Research Lab was also setting up the DIMAS array, which was 60 hydrophones in a circle to look for Russian submarine. And when I arrived and announced that I was going to put an air gun down and start going bang, 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 they impossible to have enough power. The whole camp was powered off a 13 kilowatt generator. So there was no possibility of running a diving compressor for a number of years to supply an air gun. Luckily, there was a EG&G boomer system with 7,000 joule capacity, which we set up, and I was told that I could use no more power than the camp toaster. So in any case, with General Motors, we agreed that I would fire every 5 minutes, and they had about 4 minutes to circle around the Arctic with their listing, stick their fingers in their ears, and then when the spark went off, it was a hell of it. In any case, just sort of patting myself on the back, if you look at the total amount of seismics which was available, some 4,000 kilometers were taken by the system on T3. This was compared with 1.5 times as much data which was taken by the icebreakers through 2001. So there's an awful lot of seismics of very poor quality by and large that are available in places that just no other coverage is possible. Now, here, part of my thesis consisted of writing up something that Bruce Hazen described as sediment waves. And we went through, and this was an area of bottom where you had periodic waves that we saw in the echo sounder. Underneath, everything was flat lying. There was about 200 meters of sediments there, and on top of the flat line. And part of the thesis showed that you could not form this today because there was not enough current activity. And the interesting thing was in 2005 when the hot tracks went from across the Arctic to Norway, the first multi-beam evidence of this was seen, and indicating again that there were currents there. And this is a view of the kind of thing that we got in the 12 kilocycles, taking a sounding every second. This is the kind of thing we got in my seismic profiler, and that's part of this section here. We had one place where the ice station made a loop, and we had 2 of these things that appeared to line up as far as wavelength and amplitude, and so we had a general direction of what we thought the linearity of these things was if they were sediment waves. In any case, now we come down to the sampling that was done within the Arctic. And in 2004, while I was on a visiting scientist here, ASEX drilled on the Lomonosov Ridge down to a depth of 422 meters. They went back some 55 million years, 56.2 on this indication. The interesting thing was that there was a hiatus of 20 million years on the sediments of the Lomonosov Ridge. Now, if we look at the period going back in time here, of some 700 sediment cores which were taken in the Arctic, most of them are 1 to 2 million, because the sedimentation rate today with the ice rafted debris is between 80 and 120 centimeters per year. No, per million years, excuse me. Very low sedimentation rate, a meter per million approximately. So in any case, here we were with the youngest one from the Eocene in one of the USGS heat flow cores. Here's another heat flow core that was taken here. The Canadians had a airlifted 53-day occupation, which they called Caesar, in 1983. And then here's another one of these heat flow cores here that is getting back to the late Cretaceous. So between 40 and 70 million years, we have short cores. By and large, the barrel on these things was a maximum of 4 meters generally. And we weren't taking the full length because the ice rafted debris is very grainy with sand grains and other things like this. The question is, why do we have cores that are this old? And so going on, if we look at T3's track up in the upper part of the Alpha Ridge here, here are the four cores. The area between them is 20,000 square kilometers. It's not a small area at all. And other cores that were taken out of this, of course, were showing ages of 1 to 2 million years, whatever they could get into of the ice raft debris. Here it is. The interesting thing there is I have now taken one of the few good images taken from satellites of the ice cover here, which I have draped in Global Mapper over the topography. I've put the core locations, and of intriguing interest, if we were to get up here, is that in some cases we have leads which we have followed in for distances of 800 to 1,000 kilometers. So the interesting thing would be that if we had something like the hovercraft and we got into those, we could become something like a seismic profiling Kon-Tiki, running along the lead and towing equipment. While I was on sabbatical here, Ingve Kristoffersen, who is 1 year younger than I am, and who completed his PhD at Lamont some 7 years after I did, invited me to go down to Colombia, bring all the seismic profiles, go over Bergen, and we copied them and we began looking through them, trying to figure out why these older cores were available. And the result of that was a poster that luckily did not attract too much interest in the 2006 fall EGU, because we probably would have been considered as being total maniacs. But in it, he pointed out that there is an area, an area of some 200 by 600 kilometers here, where up to 500 meters of the sediments seem to be missing from the top. That if everything was more or less flatlined down below that with the 1 kilometer blanket that we have, more or less over the highs in the Arctic, what could have caused that? And after spending a number of months looking at the data, he invited me back over. He didn't tell me why. On the way away from the airport, he whispered, "Asteroid." Nowadays, we think that it might have been a comet, because a single asteroid probably is not going to make a area of deflation that is this large. There may have been many, many cometary pieces coming into the lanyard. But in any case, here was this, and this is an example of what the disturbed sediment looked like, as opposed to where we get the blankets. And I should point out that after the Healy cruise, Ingve Kristoffersen retired, and on my way to his retirement party in Bergen, there was a 2-day meeting on Arctic drilling, which was held in Copenhagen. And the bottom line there is that there is very little chance of getting a drill vessel up there to do more drilling until such time as ages can be ascribed to some of these major reflectors, which can be followed for long distances across the Arctic. The drilling committee wants to know what the targets are going to be before they're going to put in the very large budgets for having multiple icebreakers, which will push ice away from where a drill vessel is hanging on, as happened with A6. So,
John, why do they feel like they need that information? I mean, if you drilled it, wouldn't you?
I don't know.
Well, no, actually, the most important reason is safety. You don't want to drill into what's potentially a hydrocarbon.
One of the interesting things about A6 was that they didn't drill that until several extra profiles were done. And then what they found at the back 55 million years was brackish water, much warmer ocean with duckweed, basically, the azola, which is the source of the oil in the North Slope. And of course, the oil companies have piqued up their interest, and it is suspected that there are going to be hydrocarbons throughout. But in any case, coming back from our farthest north point, we finally made this profile with the Healy with the new EM-122 432B multi-beam. And the earlier thing that had been written up on EOS was here. Here is the Healy profile, and then this is where my work from T3 located some 30,000 square kilometers of these, what we call sediment rings. So looking at that profile here, this is the chirp records put together section by section by section, and the whole topography over this part of the Alpha Mendeleev Ridge is different. And so this is a Fledermaus image that Larry made based upon that. As soon as I saw this, I began leaping up and down and saying, this is what I've been talking about, this is what I've been talking about, like a maniac. And for the first time, there were sort of looks at me as if perhaps I was compos mentis, not incompos mentis. In any case, in order to get a better view of this, we slowed the ship down a bit, and we were getting far more pings. Some of these areas here are having side slopes of up to 40 degrees.
What kind of relief we looking
50 meters by and large. The lowest ones maybe 5 meters. The wavelength certainly what we were seeing in the chirp directly under the ship was about 500 meters. And to me, this looks like the ejective field of what would be if continuing on over this way was where the asteroid impact was, or the bolide impact. Another interesting thing is in the detail of the chirp is that we have 25 meters of transparent sediment, which is absolutely conformal along here. Any core, a short core that's stuck in here is going to pick up the 1 or 2 meters of ice rafted debris. My suspicion is that if a longer core is put through that, this may very well be just the settling of the fine muds from a very muddy spot in the Arctic Ocean after the impact. No proof whatsoever, but the case that we're building up. After we began looking into this, we began running across 2 other papers that we found immensely interesting. This by Gunilla Gard appeared in 1994, and I didn't know about it until 2 years ago. And the interesting thing was when they looked through most of the Alfred Wegener Institute cores that were taken in the Eastern Arctic, they were finding nanofossils which were going back to the lower Jurassic. So continuing on here, here is the figure that they had of where the various cores are. Most of the 2000 ones are from the Wegener Institute, and the Polish Stern was primarily working in the Eastern Arctic. The area that we're talking about is here. The interesting thing is if you take Dr. Gard's indication of where reworked sediments might have come from, anything which is occurring out here is going to be blasted all over this area here. And she lists approximately 100 species from up to the Pliocene and actually recent, which are seen in these short cores. The second thing was a paper that appeared 4 years after that. Dennis Darby from Canada, who had worked up most of the cores from the Western Arctic around through this area. And his conclusion was that these spherules that were seen throughout the upper layers of these cores must have come from some sort of impact somewhere in the Canadian Arctic Islands. Again, our area of interest is more or less this area. This area here is blown up here, and you're getting to very large quantities of spherules within the cores. And these are very indicative also of some sort of bolide impact. And this is when we got the idea, okay, multi-year ice lays over this area. Several years previously, the Canadians and the Danes had tried to get in north of Greenland. using the newest Russian atomic icebreaker, the 50 Years of Victory, and had been thwarted. The 50 Years of Victory, together with the Odin, had gotten into very rough ice. They almost lost most of their seismic equipment, and it was a harrowing experience. In 2007, a fair amount of that multi-year ice went out, and it might possibly be possible to get an atomic breaker in there now, but you certainly would not have much maneuver room. Because if the ice is 4 to 6 meters thick and quasi-continuous, you won't be able to do much. So the whole idea was, even with the idea that sooner or later the Arctic is going to have no ice on it, we said, okay, let's go ahead and build a hovercraft and get over the ice. The main thing about a hovercraft is that it's a very comfortable ice station. You can weather any kind of storm in it. You have mobility. As soon as there's open water, you can go across it. You can't go past rubble ice. The blocks are put up. The hover height is about 73 centimeters, and it's not really good at speed to go over anything higher than 60 centimeters. On the other hand, pressure ridges may be continuous for long periods, but when they break apart, there's a water path to get through them. So here are the specs on the SABVABAA. It is 40 feet in length. It will fit into a container. As a matter of fact, if you take off the upper part of the propeller shroud, it will go into a C-130. It weighs 5 tons when it's empty. The official payload is 2,200 kilos. And we have been running at 3,500 now with no ill effects. For the seismics, we have an air compressor, which is fed by a hydraulic pump on the main 440 horsepower engine, which can drive a 20 cubic inch volt air gun. We have a 6-channel French digital streamer, and an air bottle where we can, at up to 190 bars, we can fill up the air bottle and get 22 shots out of it. So if we were drifting, periodically we start the engine, we fill the air bottle, and then while drifting, at which point you're not using any fuel, you can then do air gun seismics and probably get on the order of 2.5, 3.5 seconds of penetration, especially in the basins in between the ridges. In case of the chirp, we have a 4-element Knudsen 3200. The Healy actually has 16. If we're drifting, we're operating at something on the order of 10 dB below sea state 0. When you're operating on the Healy, you're probably dealing with 50 dB. Okay, we have a 12 and 200 kilocycle echo sounder. The 200 kilocycle for drifting would be very interesting for seeing what the deep scattering layer in the Arctic is doing. This is something we did on T3 for years. We have a winch, which every part of it is man-portable. The whole thing is based upon a capstan, which is hydraulically controlled, and then 1,000-meter lengths of Kevlar with a 2-ton braking strength, which are on hydraulic reels that have a take-up, but nothing under tension. And I can pick up one of these and put it on the wings of the hovercraft. Then for oceanography, there's a 500-meter single conductor cable on a hydraulic winch with Seabird CTD as well as a ADCP. And we have developed 2 autonomous seismic profiling buoys with a 5 kilojoule sparker, GPS Iridium telemetry, plus Argos location backup in the event of a failure. These are powered by methanol fuel cells, which originally came from camping vehicles for running the stuff on a Winnebago and things like that. Also, we have one SPAR 3.5 kilohertz EchoBox autonomous echo sounding buoy, and I'll show pictures of that later. Dredging, the last 2, actually 3 years have been used for dredging, bringing up basalts from the Yermak Plateau. And the dredge, these 2 dredges I can hold in my 2 hands. But they have been quite successful. Coring is a 2-meter long hydrostatically boosted core. This consists of a cylinder with a piston in the end The piston is restrained. As you go down deeper and deeper and deeper, you have hydrostatic pressure on the piston, which weighs something on the order of 2 kilos. When you're close to the bottom, you open up an umbrella, which is above it, so nothing can go up. You release the detents, and 2,500 meters of water. There's a calculated, based upon tests in 250 meters, of 13-ton weight equivalent on that core. Then beyond that, you'll see pictures of the nice drill that we have, and there's a hydraulic chainsaw for cutting apart ice, as well as a electromagnetic probe forward, which gives us an indication of ice thickness on any flow that we get on every 2 seconds. Here is the SABVABAA, and at this point the CTD winch has basically, if you were reeling it in, this would come up, lie against that platform, fall back like this, and then the hand reaches out, clamps it, and you're through with the equipment. If you wanted to take a lowering, you open up the window, you unclamp it, you reverse the hydraulics, down it goes. And we have actually used this in the middle of a flow with that going down through a seal's breathing hole. This unit out here is the transmitter and receiver for the electromagnetic pulses put out, and there's an acoustic altimeter in the center, which is telling you how high you are. This gives an indication of the kind of work that we did in our 4th year of operation. We have a website. I have a business card with the website on the back if you would like a copy of that. In any case, what's going on with the hovercraft and its Iridium phone numbers and things like that are all on the website, together with an explanation of why we're doing this. And all of this data has already been contributed to Martin Jacobson for input into the next troop count. Here's an indication of the sort of profiles we have, and of course when we're drifting, in the case of the echo box, the ice is going some 30 degrees to the direction of the wind, and of course as high pressure or low pressure systems go, you have a cyclonic flow. So quite often you're getting some sort of a 3-dimensional pattern from your drift. Okay, just looking at the various modes of operation of it, if you are on calm water at maximum power, we have gotten 85 kilometers per hour. The sweet spot is 25 knots, at which point we are burning about 35 liters per hour. Flooded ice, the kind of thing that causes anybody who's getting down on the ice from the Healy all sorts of problems. There's no problem whatsoever. And of course, with the melt, all the low spots are beginning to be filled in with water. And so water ice is the same thing for us as far as moving around. These are 2 indications of the ice conditions that we had last summer. And this kind of thing, you would move around slowly. You have to be very situationally aware so as not to run into things. In whiteout conditions, we have run up on sastrugi where we lose the bubble underneath. In that case, the craft is up like this, and this ice wall has to be built along that until you get the bubble and you can slide off. Or we have a little tiny winch that can be attached, and it can just sort of drill a hole, put a pipe down into it, and pull it off of things, or pull it up on flows which are too high. The other thing which happened last summer is a pressure ridge started to form underneath it while they were sleeping. And this was sort of exciting because the ice broke up and the equipment was going on different blocks, and they all had to be pulled back in and taken off the various ice blocks. This is sweeter sailing for the hovercraft, and of course, if we're working in the wintertime, snow is filling in a lot of these holes, and you just have to stay away from the sastrugi, rubble ice, and the pressure ridges. Here it is going through much of the areas that are really mashed up, very much like what you have in a margarita. And this kind of ice that polar bear actually has to swim through, pushing stuff away. And of course, a man cannot get across that. He has to swim to it if he's trying to walk to the pole. But the hovercraft, it means that there are not large blocks of ice picking up and you can go right over it. This is the size of the floe that you can get on. You can even get on smaller ones, and you immediately have deck area all over the place. Compared to the Healy, for instance, you can pull the throttles, stop the engine, and in less than a minute be out on the ice. And Healy, it's a matter of hours and lots of organization. Here it is on a much more stable area. We have something for generating electricity here, but we've found that it's probably more efficient in future to lay out these flexible things across the ice and generate much larger amounts of power. The deck areas are holding at maximum. We can carry something in the order of 2,500 liters of fuel, and then we have equipment stashed here, there, and yon. For the first 3 years, the governor of Spitsbergen allowed us to maintain 13 barrels north of Spitsbergen for making the run back to Longyearbyen, which is about 300 kilometers, or the 200 kilometers up to the ice. So last year, I said, no, there were too many birds in the area, we were not allowed to do it. We have to bring back our empties in any case, and so this has come back looking like Russian research vessels with automobiles all over them when they returned to pre-1993 Russia. We would have barrels just stacked up here. Here are various pictures of geophysical tests going back in past years, and on the craft itself, it's very stable, and you can lean out. And basically, you can have almost zero distance from the deck itself out to the water that you want to operate in. Here are more pictures. This is the spark array that goes along with the autonomous seismic buoy. There's a lot of seismic gear, recording gear, and everything else in the cockpit. This is the kind of record which was obtained by this drifting. And every time it goes 50 meters, the GPS indicates, okay, the time has come to fire the sparker again, and records the first second of underneath the bottom, which is then sent through the iridium back to Bergen and put into the seismic profile. Here are some of the other scenes. This is the lowering down through a seal's breathing hole. In this case, the ice was thin enough so the weight of the hovercraft has actually deflected that, and seawater has come up through the hole. Here's the gal who used that equipment to do a master's thesis. And, this is home built. Ingve Kristofferson did this in the machine shop attached to his house. And most of the equipment we have has been home built. Here's Ingve operating that with our ADCP, and it's this kind of passive equipment that can be put down while you drift during a sleep cycle. And with respect to crewing, we've debated 3 people, 2 people, what's best. 2 people don't get in each other's way. If you have 3, you can have 2 talking about the third, which is uncomfortable, or one saying, oh, I can break my leg, and the other 2 will carry me. So the 2 people, it is quite comfortable, and you don't get in each other's way. The food requirements are much, much less, of course. If you have 1 person less, you have more fuel that you can carry. Here is what the original autonomous seismic buoy was all about. Now all of this would be replaced by a box a third the size of this with a tank of methanol. More and more we are dealing with these bladders which can hold anything up to 4 cubic meters of diesel fuel. Everything we have is diesel fuel. And when you roll them up, the bladder itself is less than the weight of one 55 gallon pump. This is the ice drill, which was tested out this past summer, and this lies down on the deck, is set up, and you can then drill through the ice. And what's interesting is there's a bear. This thing is a bear magnet. And they get scared away as soon as you start the engine going. They will run away. If they are leaning across the deck where the food panniers are, then the second you start the engine, immediately we have this almost meter-wide bubble. And the air pressure may be very low, but the surface area up against the bear is such that the bear will go ass over cheek. Something like that. You do have in various reports of CCOM pictures of a bear which actually stuck his head into the driver's window. I did not bring with me the movies of that, but I showed them on the icebreaker last summer, and people were saying, "Oh my God!" In summertime, you do have snow, and then it begins to show that inside it can be totally cozy, and heating is supplied by 2 reflex Danish fishing boat stoves that provide a lot of heat. Here Ingve is crossing over a very small lead. I point out that we have one decal for the Geological Survey of Israel, and I was allowed to put that on, provided all the countries around the Arctic don't begin arguing about what the hell are the is doing. Here is the winch system with the hydraulically powered capstan here. Here is a drum with 1,000 meters. This is an A-frame that can be set up, but more and more for the dredging, the line went directly through here, and we did not have any kind of meter wheel or anything else up above. The meter wheel is on this, actually. Here it is set up for dredging. And another view with these augers, you can very quickly drill a hole down and then put a pole in to act as your anchor point. And of course, within the Arctic, because of the ice, you do not have waves, you do not have all kinds of commotion. By and large, things are pretty passive as long as you don't fall on. Come along is used with the electric winch as soon as you've got to land or whatever is behind, and these are all kind of pieces of vessel in here. It's a rock pile that they're building up. Each one of these, as I say, is 1,000 meters, and since you can put come-alongs on this, there's no reason you can't hook more and more line to it. And then you, on the other hand, on the upper parts of the Alpha Ridge, we're dealing with, say, 1,000 to 1,500 meters of water. Here's a close-up of the head that, the capstan that controls everything, animated over here. The hydraulics are anybody loves to work with hydraulics, and of course they're very sensitive and allow you complete control of them. Here are the homemade dredges. Again, getting ready to do a dredge. It's a lot different from the operations on board the Evening. Visiting polar bear, I promise. This was before somebody reached over and opened that, and I just think of these 5-inch long claws that could have gone like that and extruded the Norwegians through the window.
Justin, before you leave the dredges, you said one of the dredges had a camera. I'm quite intrigued about that.
Yeah, I don't know whether it was used, but Ingve,
It's not a conducting cable, so the
No. This is a camera that's put there with the pressure housing, and it records the whole load. Apparently. And I suspect that there are LEDs that are around it. Okay. fair amount of work went into trying to develop a autonomous echo sounding buoy, and over $500,000 of NSF funds were spent, and basically did not wind up with a working unit. We tried to continue this with the same company that in Norway that had made the seismic profiling system, and I blew another $100,000 with him, and we got a working system and an 8-page report on what had been done, most of which was boilerplate. In any case, we do know that we have that working part. So after that, we began using these SideQuest echo boxes. The more expensive one actually has all the electronics in it for generating chirp signals. And so one of the possibilities that we might have with the 3.5 kilocycle transducers that we're using is the ability to pay far more for the iridium transmission of data, short burst data, but to actually have the buoys go over into chirp mode. Chirp is going to be very important for us in that one of the things that we want to do with the coring program as soon as we have the wherewithal of getting over to the Alpha Ridge. I should say that last summer we were offered a ride in 2014 by Alpha Brigadier Institute Polish Flag. The meeting that I had with the Arctic Drilling, the chief scientists agreed that most likely it would be possible for us to get a one-way trip and then drift out later, plan B. And secondly, and the most difficult part, because no oil, lubricants, or anything else are allowed on the ice these days, even though T3 had 80,000 barrels on it when I left, would be to leave us for 2 cubic meters of diesel fuel for every month of occupation. And the Germans' attitude, well, there isn't German oil, it's from other regions. But we don't have a problem with the empties if we are using the bladders, and we bring the bladders back with us. So in any case, this is the guts of the buoy that we hope to set out next summer. And then beyond that, SideQuest says that there's no reason that for on the order of $5,000, these things can run up to $25,000, that the inner electronics which take care of that cannot be taken out and buoyized in such a way that we can start having something that can be put into the Southeast Pacific for getting far more data for calibrating the satellite altimetry, which is important to JEPCO. Also for sticking into Antarctica, the original idea was if we had these things encapsulated in buoys that could be airdropped or put in by icebreakers, during the lifetime of a buoy, it could actually go around in the ice around Antarctica and make a full circle. In the Arctic, we have the ideal thing for this in hovercraft that can, I would say, within a half an hour, you could install a buoy. Drilling a hole, putting it down, and then taking it off. And unlike the Healy, there's always the risk with the Healy after you drill a hole and put a buoy in, that as the ship takes off, the crack goes right through that hole. Dale Shays has been running for the last couple of years between northern Greenland and the North Pole on the Lamont program of running a CTD carousel through a 12-inch hole. And instead of being a very large thing like that, it's something about 11-inch diameter with collector, 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 collector. And from this tent here, they're operating through that hole, and what the plan would be to, if these are the various places where they've gathered water samples for measuring trace elements, to this spring to put out one of those buoys somewhere around in here where a fuel cache is, allow it to operate for the few weeks that they are doing these flights. Each time they're coming back and immediately doing the chemistry from the water sample. They won't hold heat until they get back to Lamont. And then when they clean up their fuel cache to perhaps land some other place, put the buoy in, and we will kiss goodbye a echo box. And we'll try to get several years kilometers of drifting around in this area which has seen almost no occupation whatsoever. I can't think of anything that I might have forgotten. Dave Monahan gave me this classic talk ending. Are there any questions?
I have a question about when you were on the drifting ice back in the 70s. Did you guys drill cores through the middle of the ice down into the sediment?
To see what the glaciology of the ice station was, or?
Did you drill into the seafloor?
Drill, definitely not, but with the huts, in 3 or 4 days, 2 guys working full time in 25 degrees below zero could make a 4 foot by 4 foot hole through 6 meters of ice.
Okay.
The touchy part was that when you got near the bottom, the ice is not solid and seawater begins to come in. So the solution there is to put 1 pound of Petron down in the hole, blow out the bottom, and then scoop out all the ice that comes up. After that, a hydro hut is put on top of it, and then heating cables are used, or these heat mats that you have in a truck stop where they have the food out for 24 hours to warm it. These kind of things are down in the hole. One of the tricky things is that the fresh water, which is coming down off the ice station, goes down underneath that ice there, and the temperature of the Central Arctic Ocean can get down to -2 centigrade.
Go back to your slide and show them. They then set a big tripod in there, and they can take the full distance over gravity.
How fast did they move the actual ice?
The average was about, I think, 5.8 kilometers per day, and nowadays it gets up to 20 kilometers per day.
Oh, there we go. So those.
So here's Lamont's hydro hut. This building here is about the height of this room, and then we have an additional probably 4.5 meters up into the where the A-frame is. But one of the problems is the latter part of the summer you can have another frozen ice edge underneath. And if you're using the Ewing piston core, what you do is you have a pipe with a very sharp end, and you have lead weights, and you have a glider release attached to an arm with a small flagger core on it here. And the whole idea is you get down close to the bottom, the weight of the flagger core is taken up by the bottom. The spring on the glider release goes up. This releases the 3/4 ton or 1 ton weight of the core. It goes down just at the point when it hits the sediments. There's a chain which is attached to the core plug which starts going up. It stays in place, the core one goes down, and essentially you're hoping that the core is going down just as fast as you are pulling sediment in. Now, with this ice edge down there, we didn't know anything about the ice edge, and so lowering the core, having primed it and everything else like that, it got down a few meters. The glider arm hit that, went like this. I was asleep when one of the guys that was working that summer came out absolutely white in the face. And apparently the building had gone in.
Yeah.
But we did not lose the core, and we did not lose the wire, and we did not lose anything else. We learned an awful lot about putting 2x4s down and trying to find out whether or not there was something down.
What's really hard to tell from this picture is that where those huts are, that's sea ice. So that's just 3, 4, 5, 6 meters thick. It's monkey right there in this case. But where the buildings are, that's a piece of
That had 40 meters of ice under us.
It's a piece of ice
under us here.
that broke off. So that's 40.
And all our drinking water was either up until September, more or less, you could run a pipe into ice-covered lakes of melt things. After that, all during the winter, it's a matter of cutting out ice with a chainsaw, bringing it up and putting it in the trailer where the stove is going full blast, and then taking a shower once a month.
John, this asteroid or comets or whatever, when did this occur? And is there any corroborating evidence?
One of these cores has, I think, 60 centimeters of more recent ice-rafted debris on top of it. So trying to chase down the age would mean, as we gather more and more cores in places that have not had any bottom current activity or anything like that. I mean, bottom currents that we were measuring with the tripod that we put down with measuring equipment were on the order of a few centimeters per second. As a matter of fact, something that had a pinwheel like that didn't work, and so we began putting these plumber's leak finders. Put out some dye, and then you see where the dye is going. It's that slow, and of course you need, what, 30 to 50 centimeters per second in order to start moving grainy sediment.
John, I love your talk. It's great.
I try to change it.
Yeah, I want to talk about the geology, but in the area you're going to is now called the Alpha Ridge. In 1979 paper, you referred to, as we all did, the Alpha Cordillera.
Yeah.
Would you just talk a bit for the students' benefit about the evolution of that name, from Cordillera to Ridge?
I don't know how that happened, actually. This is what it was referred to. Then I went off to Israel and began working in the Mediterranean. That was probably, Peter Vogt had used that name on his thesis. I think that Alan Beale used that on his thesis in the first map of the Arctic Ocean basin.
Which thing? Peter did.
Probably Alpha
Cordillera was quite a while.
I've never heard that.
And
I hadn't heard that.
Yeah.
But the Russians were working on the other end, which is the Mendeleev Ridge. And in 1966, Bruce Hazen met together with the Russians and said, look, we have our own set of names for the Arctic, but let's try to unify that. And North Pole 8 had discovered what they thought was an abyssal gap. And so Bruce Hazen, with a wry smile, proposed the name of the cooperation gap for the demarcation line between the Mendeleev and the Alpha Ridge, which was discovered by my thesis professor, Ken Hogan. And that was named after Ice Station Alpha, which was the 1957-58 IPY, International Polar Year, ice station. There was an ice station Alpha. T3 may have been prior to Alpha, but it was called Ice Station Bravo. And then there was Ice Station Charlie also.
Cooperation gap doesn't exist.
Cooperation gap does not exist. As a matter of fact,
Either politically or.
So what led you to believe that an asteroid impact had occurred in that area, before you had even taken sediment cores? Or you were just looking
before
at
sediment, no, we haven't taken sediment cores yet.
Oh,
We're
okay.
still waiting to see how we get the 1,500 kilometers out there. We can carry enough fuel to get a third of the way.
What does it make you think the asteroid? I didn't see the.
But you said you're hypothesizing this from your
Something is
seismic.
removed. The seismic shows. I mean, we have a sort of standard section
Mhm.
that you have draped across the Arctic with some neotectonics and some reworking here, there, and yon, and slumps and slides and stuff like that. The question is, when you look at that, you discover that up to 500 meters of that 1,000+ meter blanket is missing,
Okay.
and it's the upper part. And the first thing you would think is, oh, there's been massive erosion. Well, okay, this isn't a bad idea. Where did it go to? But what would have caused the massive erosion? There's also an interesting thing. I had one seismic profile where I was getting 3.5 seconds of penetration in the Mendeleev plain, which is between the Mendeleev ridge itself and the Chukchi borderline. Larry more or less proved that the Mendeleev plain probably isn't a plain. It's too steep a grade. But in any case, some, I think, 2.5 seconds down, and flatline, 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 flatline. Again, stuff like this. Now,
But I think, but
there's one known, or pretty well presumed, asteroid impact area in the ocean. 71% of the planet. And it's probable that all of these bodies coming in the hollouts don't have some sort of navigation to say, oh, I don't want the blue, I want the green.
the part that maybe the students aren't connecting is that when you see stuff like this on the bottom, or stuff like this. This is not normal. And to get something like that implies a very, very corrugated type seafloor of some sort, and a little bit of multi-beam that we had showing this. Now, that when they first saw it, they thought bed forms, because that's indeed the easiest way to make that. But
Well, when
these are
Bruce
not-
Hazen
not
says
regular.
it's sediment waves.
Everybody says, of course.
Oh, yes, yes.
But that was based on just intuition. But when you see it, it's much more chaotic than regular waves. So.
To me, this doesn't look, it looks too sparse.
To me, this
To me,
reminds
you look
what
at
you get
anything.
when you're operating a snowplow and you have thick snow and you ram into it. Now, before I came here, I spent some time with Dallas Abbott, who's been working on these super tsunamis and the chevron blocks of deep ocean sediments which are on the coast of Mozambique. And she has given me the description of a place where I can go and start doing modeling impact. And she says that I've got to try to figure out what the major axes of this what we've been calling a rectangular area are. And also she suspects that there may be something in the magnetics of that area which would tell us something. I don't believe that that's the case.
But there is a place where there is topography like this, and that's the scablands of Idaho. And what that was the catastrophic failure of a glacial lake, where
Like Missoula.
where millions of gallons of water instantaneously rushed out, and we created bed forms that are 50 to 100 meters made of gravel. And it's just unbelievable. It goes on for hundreds and hundreds of square kilometers over South Dakota, Idaho, places like that.
Kettle holes that you could put a bus into. Blocks the size of a house
That
that
is.
are up on top of the
Yeah,
plateau.
I'm pretty sure it's in South Dakota too. Scablands, I think they're South.
That's the band.
No, the scablands.
Eastern Washington.
Yeah,
Washington.
Washington, Utah. Yeah, they're between Missoula and the
Utah's
ocean.
too far south.
And South Dakota is the other direction.
The size of
Out there somewhere. In plate tectonics.
Presumably, Lake Missoula was in Montana. Between Montana.
But there's a place on the seafloor where we've seen this too, and that's on the Laurentian Fan, where there are 50 to 100 meter high waves of gravel. They're more regular than this. They're not as chaotic, but they're same sort of dimensions and literally made out of cobbles and gravel. And that was the result of a 1,000-meter thick turbidity current, the one that sequentially broke the cables, the telegraph cables in 1929.
But John, you have no idea when this occurred.
Our assumption is within the last 2 million years.
Okay, that's what I was.
We have the number of sediment about it.
Yeah, because if you look at
It's according to how much sediment we have
if you
from
look here,
just
there's
this
no
one.
sediment on
Yeah, so it's
it. But
But
there are
there's
places-
25 meters of this. I suspect you get into that. This is what very quickly,
When you show
2
that
weeks.
picture, go back to the picture that has the transparent layer.
Well, you can see it off over
Well,
here.
yeah, there it is.
And then we'll see if there's a
One more.
Yeah.
There, yeah.
But, there's a lot of geometry that needs to be worked out here, because, if you look at some places, you go back to this undisturbed, or maybe redeposited if you want it that way. And then you go back to the chaotic, and then back to undisturbed, and we really need a three-dimensional picture of it, not just a single crossing. Kind of put together the.
The topography is somewhat reminiscent also of the big failures of Hawaii. The big, the
third of the
So like
United
Kanama
States
Bay?
area
Yeah.
of half the island.
these,
going
yeah,
down.
these great big polys are called now, the part of the Silver Main, but the whole island collapsed, probably by over construction, right into the mold itself. And if you go out in the distal ends of those things, you see huge blocks when you're closer to the island, but as you go out in the distal ends, you find this kind of topography.
Can't just fly a drilling rig out.
Well, you could. I mean, yeah, but it's a million here, a million there. And, now, the spending of $1.5 or a bit more than that $1 million has labeled us as being absolutely out of our mind.
Thank you, John, just confirm that, that's all. Not to worry.
What kind of abrasion do you get on the skirt on the front of that thing when you're moving across the ice?
We have 20,000 kilometers, and there are 100 fingers which are sort of look like this that make contact with the ground. And we've replaced 2. The general rule when you're dealing with beaches and mud flats and areas that are not up in the ice are that you have to change them about as often as you rotate your tires, every 35,000 miles.
Yeah, but that's not very abrasive stuff compared to ice.
Well, the ice has snow on top of it.
So that's not, that snow's not being disturbed by that?
Basically, it looks like you'd run over it with a whitewash brush.
Huh.
Yeah, that shows the progress. Like when we tried it in 1970, we got less than 200 miles in the skirts. And you get
Those monsters with the non-ducted prop and little Eskimo kids running around.
I know what the second part. I don't remember the second part.
At night when you're sitting there asleep in your hovercraft and the skirt is lowered, does it not freeze to the?
We were worried about that. As soon as you fire up the engine, up you go.
It just rips
But
it out.
thus far, we've worked during the summertime, and in the summertime, everything's melting. I mean, you have more heat energy coming in than what you have at the equator when the sun is directly overhead. 24 hours a day.
Well, freezing most of the time, doesn't it?
This summer, most of the time, it was only the latter part of our cruise that it's the wind that makes you feel cold, but the temperature is anything up to 4 or 5 degrees above.
I mean, that's what it looked like in the photos.
I mean, we did have worries that we have 2 skids underneath, that these might freeze as well. The fact is, the second you started out, 40% of your power goes to lift, 60% for propulsion. And that, if you take a strip this wide, which is, say, 35 feet long, and you take the amount of air pressure that you're putting down, it would be pretty hard to hold it down. But in any case, we do carry a couple of 2x4s, which are useful for doing various things. And if you're going to stay for quite a while and expect 25 or 30 below zero, then at that point, you probably put 2x4s out, run it on the 2x4s instead of down on the If you go to our website, you can see inside what's going on.
Maria has a question.
Yeah, you had a lot of successes. What were your biggest failures? Can you talk about problems you might have had? Or not?
This is an airplane.
You don't have 2 weeks, right?
Yeah.
If I want to go
Biggest.
there, and the wind is blowing this way, I travel like this. Okay, I crab.
Mm-hmm.
And we had one time when they were ready to come back and they had to wait for 5 days for a headwind to abate because there was a 25-knot headwind, which means they could have sat in the sweet spot in the same place. Burning fuel. The first real problem that we had was that there is a clutch which disconnects from the engine to the lift fan, clutch, and then a belt going to the propulsion fan. And the clutch burned out after 318 hours. And this was designed for 30,000 hours at full power. Oh. Big argument began because the Timken bearings had never been lubricated. And we have a strict schedule of climbing underneath with a grease gun and lubricating everything. But what was missing was a hole so that you do this, you see stuff coming out, and never mind that it goes on the ice, you say, it's lubricated. And so the company wanted to, the companies began facing off on who was responsible. I said, look, I'm not in this to make the world perfect. We want to get up the Alpha Ridge. And so they put in another system. But the thing that happened was that crapped out just before they got to northern Spitzbergen. They were in shallow water. They were lift fan worked. So I mean, you just had to lean on it. It moved, but not against the wind. And as soon as they got near the shore, then they took some drift logs, pulled out the winch cable, and pulled it up on the beach, and then got on the horn and found that one of the ships that was operating in northern Svalbard was available for charter for $15,000. And then began the comic part, because the ship could not get in anywhere near the hovercraft, and so one of these children's blow-up life rafts came in with a tiny little putt-putt. And we went up in the lift fan, and they took over, and you had this little tiny thing pulling the great big hovercraft behind it. They got out to this landing craft type thing, which picked it up, put it in, and brought us back, and we paid the $15,000 charter, and everything was hunky-dory. Last summer, without having a chance to refuel, you refueled in the Ellison, which is the science village, about 100 kilometers short of northern Spitzbergen. We ran out, or they ran out. I haven't been on it on the ice. I write checks. Anyway, they ran out about, I think, 50 kilometers north of Spitzbergen of fuel. And so again, on the Iridium, they contacted one of the research vessels that's operating. It gave them 600 liters of fuel, which then allowed them to get down to the Allison and refuel. So they've had that. They've also had another thing that made us nervous as hell was that one of the actuators for the rudder behind the propulsion fan was showing signs of leakage. And so we ordered the exact same part from Griffin, who makes these things, and we got a spare part. Okay, let's change it. We discovered that every single fitting on that had a different size of thread. Now, Ingve is a mechanical genius who keeps air guns going and things like that, and so we were able to order enough parts so we could gerrymander that. But in many cases, we have to be carrying, say, up to 50 kilos of tools for keeping it going. I talked with him 2 days ago, and he was up there making sure that we have all the parts for the electromagnetic probe. And what we may wind up doing this summer at Station Nord in Greenland. The Norwegian, Danish admiral has asked that we go over there and survey the shorefast ice near Station Nord that was set up during the Cold War. And the whole air station was set up by air. Fuel is exceedingly expensive there. And in order to get sea lift in there where they can, like the Russian tanker that's just come in delivering, 1.4 million gallons to Nome, if they can get a barge in there, this is fine. And we believe that a nuclear breaker can probably smash apart that part and bring in something. The thing is that they don't want to go charging against the shorefast ice, not knowing what the hydrography is. And so what they want us to do is they will give us a ride over, and then we will run around on this autostrada of shorefast ice and drilling holes and taking soundings to do that. So this is one of our possibilities for this summer.
Okay.
We always figured that in 10 hours we could be across in Greenland, across the Atlantic in 10 hours. The main comeuppance there was that the weather cycles are maybe every 50 kilometers. So you can have the really flat calm where we get to our highest speeds. Over 50 kilometers, and the next thing you know, you have waves coming over the front, which is not nice. Thank you very much.
I think I just wanted to say that I think what particularly the students are getting is a glimpse at real exploration in one of the most difficult places to work. And I think we're really fortunate that John is both a scientist and also a patron of the exploration. And that's what makes it work together. So, it's special day.